Welcome to the Math 140. This is the first video in a series of videos I'll be creating over the quarter to help you understand the concepts that I will be teaching. So before we get started, I want to emphasize something that is big in my teaching style. In math, I think there's a lot of problems with people tend to have what I call a problem recognition approach to understanding math rather than a conceptual understanding. And I really emphasize conceptual understanding as I teach, and I think it's a much better way, much more efficient way to learn math. So I may be stretching some of you in that regard this quarter. And the difference is that in problem recognition, students, they have a tendency to just look at the problem and they try to recognize problems that they've done in the past that look like this, and then they just do the same thing they did last time they saw a problem like that. Whereas conceptual understanding is more along the lines of you learn concepts, study vocabulary, and so when you come to a new problem, you read the directions to make sure you understand all the vocabulary in the directions, and you use the concepts and the skills that you've developed to solve the problem. And so this, of course, is a deeper understanding, and you're actually doing something. You understand why you're doing it, whereas this is more of a kind of a magical memorization type thing where you're saying, I remember what I did last time I saw a problem that looked like this. And this is why a lot of people say, I'm not very good at math because I can't memorize formulas. I personally am terrible at memorizing things, and I am very good at math. So memory is not really a big key for math. It's actually more understanding is what's really important. So to begin with, I wanted to run you through, this is probably something you've seen before, but it's important to understand the different numbers that we'll be dealing with. The numbers are broken into categories. And the biggest, broadest category is complex numbers. All the numbers that we will be dealing with fall under the heading of complex numbers. And so then the complex numbers, as you can see in this little chart, are broken into two types of numbers. There's real numbers and imaginary numbers. Complex numbers in general can be written like this, a plus bi, where a is a number and b is a number, and I is the some of you may not have been exposed to it yet, but I is the square root of -1. So we will not be done with imaginary numbers much at all, or very little in this class. You'll see them more in 141, which is the class after this. But imaginary numbers are numbers that have something other than 0 for b. So if b is 0, if you have a complex number where b is 0, then you have a real number. So another way to think of it is real numbers do not involve the I, imaginary numbers do. So an imaginary number could be like 3i, or 2 plus 5i, or 1/2 minus 2/3 I. Okay, real numbers are the numbers that you know. Okay, so now the real numbers are broken into two types of numbers, rational and irrational. Rational numbers are numbers that can be expressed as a fraction. So 2/3, 5, 5/9, 1 3/5. All these things are numbers that can be expressed as fractions. Even, for example, 0.33 repeating. That is a rational number because it can be expressed as 1/3. It's the same thing as 1/3. Okay, so any number that can be expressed as a fraction is a rational number. So then they may ask, well, what does that leave for irrational numbers? Generally, the numbers that are never-ending decimals that are non-repeating. So some of the famous irrational numbers are pi, and e. You may be familiar with e. If you're not, you'll definitely spend a lot of time with e in 141. But numbers just like 0.315723814, a never-ending decimal that has no pattern to it. You see that 0.333 repeating has a pattern to it. I mean, it's also never-ending, but it does have a pattern to it. So any repeating decimal can be changed to a fraction. Okay, so that's the difference between rational and irrational. Then we have integers. Integers are, I'm going to skip over them for a second and come back to them. Whole numbers are all the numbers that we use to count with plus 0. So normally when you count, you say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And if we just add a 0 to that, that would be the list of all the whole numbers. Okay, so, etc. And then coming back to integers, integers are the whole numbers and their opposites. So that would include negative numbers too, like -2, -1, 0, 1, 2, 3, etc., and etc. that way. So notice there's no, we're not including any of the numbers between 0 and 1. We all know that there's an infinite number of numbers between 0 and 1, but they're not included in the integers. Okay? You'd have to go to the rational and the irrational to discuss all those numbers in between there. Okay? But notice the integers are included in the rationals, because I can express -2 as -2/1. I can express it as a fraction. And all rationals are included in the real numbers and in the complex. So you see how this hierarchy works. Integers are not a part of the irrational numbers. They're only a part of the rational numbers. Okay? And notice none of these are included in the imaginary numbers. Okay. So that's the breakdown of different types of numbers. You hopefully have been exposed to that before, but I just want to remind you of that because those are vocabulary words that I'll be throwing out at you. So you need to know the difference between an integer and a whole number, or an integer and a rational number. Okay? So the other thing that we need to talk about vocabulary-wise is, I just said that in conceptual understanding, we read directions, and it's important to understand what the directions mean. So for example, the word simplify. Simplify. That's often you find that in directions. So you might see a number or expression that looks like this. 3 plus, oh, come on. My thing's skipping on me. 3 plus 2 times 5 divided by 4, and we'll maybe put -3 in there or something like that. Okay? So simplify means, usually it refers to an expression. So you have an expression, and basically what it's saying is write it in its simplest form. Okay? So when you see simplify, you need to understand what that means, because what a lot of people do is they'll see something like this and they'll say, what do I do with it? Well, it just says simplify. I don't know what that means. So when it says to simplify the following expressions, that means they're really looking for an answer, but it's just the simplest version of this. You know, as we all know, 3 plus 5 is the same thing as 8, right? Well, which one of those is a simpler way to write them? Well, 8 is a simpler way to write this number than 3 plus 5. We could have also written it as 16 divided by 2, or we could have also written it as 2 times 4 times 1. Right? There's a lot of different ways to write 8, but the simplest way to write it is 8. Okay? And of course, there's rules in mathematics that you've been exposed to as you go along that decide for you what simplest looks like. So in this case, for example, we'd want to simplify this. Now, when we start doing operations, which we're being asked to do here, we also have to keep in mind order of operations. Operations. And hopefully you remember that. There's a nice little acronym that helps us kind of remind us of the order of operations. PIMDOS, although it's a little bit misleading. So this is just an acronym that reminds us of when we're doing, when we're simplifying an expression where there's mixed operations. What I mean by mixed is, notice we have a plus here, a multiplication here, a subtraction there, and a division in this bar. So there's a bunch of different operations mixed together. So order of operation tells us that we do all parentheses first, then we do exponents, and then, and this is the part that's a little bit misleading, we do multiplication and division third, and addition and subtraction fourth. So in other words, if we have multiplication and division both in the expression, we do both of them, whichever comes first from left to right. So in this case, for example, there's a few confusing things about it like this because it looks like there's no parentheses in this, which there aren't, but really we should have parentheses includes all grouping symbols. So this is actually all grouping symbols, and there's more than grouping symbols besides parentheses. There's absolute value. There's a fraction bar. This is a grouping symbol. That means we do the top first and the bottom. I mean, you do the top and the bottom before you do the division, because that division bar is a grouping symbol. So it doesn't fall under division in this category. It actually falls under the P for grouping symbols. So anyway, if we were to do this, we would do multiplication first. So 2 times 5 is 10. So this would be 3 plus 10 minus 3 over 4. And then we do addition and subtraction next, because remember, this is a grouping symbol. We have to do the stuff on top and bottom first. So then we just go from left to right. 3 plus 10 is 13. 13 minus 3 is 10. So we end up with 10 fourths. Now, we would all agree that this 10 fourths is simpler than that as far as expressing this this number or this value here, right? But there's also some rules that you've picked up along the way that when you're writing a fraction, it's simplest to write it in its reduced form. So when you write a fraction like this, we would say, is there two numbers that'll divide into both the top and bottom? In this case, 2 will divide into both top and bottom. So I could rewrite this as 5 over 2. And that would be simplest form. Now, somewhere in your grade school days, someone might have said that it's proper to write this as a mixed number, 2 and 1/2. Well, that is not a universally accepted as simplest. In this class, unless there's a reason to write like this, I would consider this to be simplest form. And that's true in, for the most part as you go up further up in mathematics, higher level mathematics. The mixed number is useful in some situations, but often the improper fraction is the more accepted style. Okay, so important to understand what simplifying means. How is that different, for example, from evaluate? Sometimes you'll see evaluate. Well, evaluate, like it sounds, it means to tell the value of this certain expression. So you could say 3 plus 4 times 5 over, well, I forgot what I did before. Yeah, it was like that. So I could say evaluate the following expression. That would mean that I need to come up with one number that represents the value of this expression. So essentially, I would do the same thing I did up here. I would go through the same process, and I'd end up with a 5/2. That would be evaluating it. We often say evaluate when we have a expression like 3x plus 2y, and we say evaluate the following when x equals 2 and y equals 3. So here's an expression. If I asked you to evaluate right now, you'd say, well, I don't know how much it's worth. But then when I say evaluate the following when x equals 2 and y equals 3, oh, so that means basically what it's telling you is you can replace x with 2 because now we know what it is. And we can replace y with, what do we say, 3 because now we know what it is. And now you can evaluate this expression. So that'd be 6 plus 6, which is 12. Okay? So that's what evaluate means. It can mean the same thing as simplify, but often we use the term evaluate in directions in a situation like this, where we have an expression with variables in it, and we get some secret inside information of what those values, variables, what their value is, so we can actually evaluate the entire expression. Which reminds me of variables. What is a variable? I know, again, you've all been exposed to it, but I just want to make sure. Remember, a variable is basically a placeholder in an expression. or equation. So, for example, we're saying, well, we know that I have to multiply 3 times something, and then I have to add 5 to it, but I don't know what the something is. So what we do there is we put a little x, right? So those are too much of a gap there. So 3x plus 5. So this is saying, I know that for some reason in a certain circumstances, I'm going to have to multiply 3 by something and then add 5 to it. But I don't know what the something is yet. So we use a variable to hold the place of that something. Oftentimes you'll say, you read a word problem in a math book where it says 2 times a number plus the number squared. So in that case, 2 times a number, I don't know what the number is, so I put a variable, plus the number squared. So since we already called the number x, if we're talking about the same number, we can use it again as x. So we'd go like that. Now, if it would have said 2 times a number plus a different number squared, then we'd have to use a different variable. We cannot use x twice in the same expression if the x isn't representing the same value. Okay, so that's important to remember about variables. If I have 15 x's in one expression, every one of those x's have to represent the same number. You can't have x be 2 one time and then later in the expression x be 5 or 1/2 or 0.7 or whatever. So if we want to represent different numbers, if we want to hold the place for different numbers, we have to have different variables. Okay? So that's a quick rundown of kind of a little opening introduction to the class. Again, the emphasis is some of you already kind of have a conceptual understanding. That's the way you approach math. And some of you don't. Some of you are still really just going by not really understanding the concepts, but just taking furious notes and memorizing problems, the way they look and what to do with them. So the people that are in that camp, I'm going to encourage you to move more towards really understanding concepts. And so if you hear something in this video that you don't understand, or if you're in class and you hear something you don't understand, I really encourage you to stop the video, go back and replay it, or send me an email, or ask me the next day in class. Make sure you understand everything I'm doing and why I'm doing it. You don't want to just say, well, I don't understand what he's doing there, but I can memorize what he did and do it later. Because the chances are there's going to be problems that look very similar to something you did with different directions on them, and you'll have to do something different. So you really have to focus in on understanding the concepts rather than just recognizing the way different problems look. Okay, I'm going to try to keep these videos fairly short so you can watch them at a short time and digest them and maybe watch them a couple times if you need to. So I'm going to end this video here, and then I'll pick up again on the next video. We'll begin talking about the different types of expressions that we're going to have to simplify. All right.